Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alright, so we meet again in this video. So basically in this video we will discuss the solution for some of the question in tutorial 3 and tutorial 4. Alright, so let's look on the first question. So this question is regarding tutorial 3, question number 9. Alright, in this question, so basically we are given 3 line charge density, right? So this is that reside on the y-axis, and this line charge density having coordinate as shown in this figure. Alright, so basically this line charge density is in direction of parallel with the z-axis. So whereas we have a y-axis here, so x-axis here, and the z-axis in this point. Alright, so toward inside this paper. So we need to find the value or the expression for the electric field intensity on the point P. And this point P is given as a coordinate of A0. Alright, so the value for each line charge density as be given in this question is equal to rho L1 is equal to 3 nanocoulomb per meter, rho L2 is equal to minus 3 coulomb per meter, and rho L3 is equal to 3 nanocoulomb per meter. And then we need to find the expression of electric field intensity on this point, and we need to evaluate the electric field intensity in a point of given here. So A is equal to 2 cm and B is equal to 1 cm. Alright, so at this point, so basically we know that the electric field intensity is given by this formula. So we have a total for electric field intensity is equal to vector E1. So vector E1 is the electric field intensity produced by the first line charge density. So plus the vector of E2. So this one is the field intensity so produced by the rho L2, and plus vector E3. So this one is 3. So the vector of E3 is the vector of electric field intensity so produced by our rho L3 or the third line charge density. Alright, so before we can solve this expression, so basically so we need to find what is the expression that represent each vector of E as shown in this equation. Alright, so in order to solve that, so let's consider Gauss law. So this is the expression that represent Gauss law. So we have closed integration of surface, so vector of D dot vector of ds is equal to Q. So Q is the total charge, and because of in this question, so the charge value is given in the by using density value, which is line charge density. So we can find the total charge by considering this line charge density is given by this expression. So whereas integration of L or line integration, so rho L dot dl. Okay, so from this expression, so the general solution for this integration is given by this formula, which is Q is equal to rho L multiplied by H. So whereas this H is represent the length of each rho L. Alright, so once we get the expression for Q here, so basically later on we will use this expression to replace inside this Q parameter inside that exists in the Gauss law equation. Alright, so let's say we have one line charge density here. So generally, so we assume that our rho L or our line charge density so produce a cylindrical shape of electric field intensity and electric flux density. So this is our line charge density, and this is shaped for vector of E and the vector of D. Okay, so because of that, So the general expression for the vector of D can be expressed as this one. So whereas the vector of D is equal to r cap multiplied by dr. And because of that, so we take that in r cap direction, so the vector for ds to be used inside this formula is given by this expression. So whereas the vector of ds is equal to r cap r d phi and dz. Alright, so by considering this side of a Gauss law expression, so basically in order to solve it, so we need to perform this series of formula. So first we need to perform a surface integration of the vector of d dot vector of ds on the top surface. Okay, so if we refer back to this shape of the electric field and electric flux shape, so first we need to perform the integration of surface on the top side. Okay, so plus with the integration of surface on the bottom side, so this side, and plus surface integration of d dot ds in side. Okay, so side surface here, so we have the side surface. So however, so since the flux density or the vector of flux density is only exists on the r cap direction, right? So in this direction, on the side direction, so therefore if we perform the integration of surface on the top and the bottom, so these two expression will result equal to 0. So that's why in order to solve this expression, so we only consider on the surface side, integration of surface on the side only. Alright, so therefore we will have the closed integration of surface vector of d dot vector of ds is equal to surface integration on the side, so r cap dr dot with r cap r d flux and dz. Alright, so inside this surface integration, so we need to perform double integration. So first is from z is equal to from 0 until h, and the second integration is phi is equal to 0 until 2 pi. So by solving this integration, so we will have the expression that the solution for this expression is given by this formula. So dr 2 pi h multiplied by r. Alright, okay, so because of we have been solved the both side of the Gauss law. Okay, so this is our Gauss law equation. So on this side, the solution for this side is given by this expression, so which is dr 2 pi hr, and the solution for the q is given by this step, so we have rho lh, and if we put in this way, so we can have our expression for dr is equal to rho l divided by 2 pi r. And if we put the expression of dr inside the vector, inside the general expression for the vector that has been shown earlier, so we will have the vector of d is represented by this expression. So r cap rho l divided by 2 pi r, and the unit for this vector is a coulomb per meter square. Okay, and because of we have a relationship between d and e, so we have vector of d is equal to epsilon e, or epsilon multiplied by the vector of e. So we can find the expression for the vector of e, or electric field intensity, is equal to this expression. So whereas the vector of e is equal to r cap rho l divided by 2 pi epsilon r, and the unit for this vector is a volt per meter. Alright, so then we need to consider, or we need to derive the electric field intensity for each vector of electric field intensity, so E1, E2 and E3. Alright, so let's consider the expression for the vector of E2 first, okay, because this vector is only one component of x, so the solution is quite straightforward. Alright, so from this from the expression for the electric field intensity, so this is our unit vector. Okay, and by looking into this direction of the vector, So we can see that the unit vector of r is equal to x cap. Okay, so because we have only direction in terms of x component only, and in this case the r, so here, so this is the distance, so distance between our charge and our test point. Okay, so in this case is equal to point P. So the distance between these two components is equal to A. So that's why from this expression, so we can rewrite the expression that represent electric field intensity, or the vector for the E for the rho L2 is equal to this expression. So we have x cap. So this is the value for our line charge density is equal to minus 3 nano. So divided by 2 pi epsilon and multiplied by A, and the unit of it is equal to volt per meter. Alright, so however for the rho L1 and the rho L3, so this is the vector of electric field intensity, okay, so produced by this rho L3. Alright, so at the same time, so this is the direction of the vector of electric field intensity, so vector of E1, basically produced by this rho L1. Alright, so in order to derive, or in order to express our unit vector here, so the unit vector r cap is equal to vector of r1. So the vector of r1 is the vector that represent direction and distance between our charge and our test point, so divided by its magnitude. Okay, or in a perspective of rho L3, so we will have expression for unit vector is equal to vector of r3. So this is our vector of r3 that represent the distance and direction between our charge and our test point. So vector of r3 divided by its amplitude. Alright, so based on this setting, so let's see, so how can we express our vector of r1? So the vector of r1 is travel from this point to this point, right? So that's why, right, for the x cap component first, so we need to make a minus with a 0. Okay, so this is for the x component for this particular vector. So we have x cap a plus 0 minus b, so we will have a positive b. So that's why on the y cap component, so we will have plus yb. So from the expression for the vector, so this is the amplitude of it, so a squared plus b squared and square root of it, and this distance as well will be take as the expression that represent our r here. So similar to the vector of r3, so we have, this is our vector r3. So the vector of r3 will be start from this point, so 0b to the a0, and then because of this fact, so this is the expression that represent our vector r3, and this is our amplitude for the vector of r3. And similar like the previous case, so we will have this expression also represent our value for the r, so here, so distance between charge and our test point. And based on this fact, so we can derive our expression for electric field intensity that produced by our rho L1 is equal to this one, so 3n, so 3 nano, so divided by 2 pi epsilon, so dot with 1 divided by a squared plus b squared and then square it 2. So this one is the expression for the r, so for the r here, okay, to replace with the r here, and then dot with the unit vector, okay, so which is the r cap here. So we will have, this is the expression that represent our vector of E that represent by our rho L1. So the unit of it is volt per meter. So similar technique that we use in order to derive the vector for the electric field intensity, so produced by the rho L3. So this is the expression that we will have. So the unit of it is equal to volt per meter. And in order to find the expression or the electric field, total electric field intensity, so produced on this point, so we need to add all the expression that we has been derived just now together. Alright, so we will have, so the vector of the total vector of the total electric field intensity, the vector of ET is equal to x cap minus 3 nano, so divided by 2 pi epsilon A. So this one is the electric field produced by rho L2, so plus 3 nano, so divided by 2 pi epsilon A squared plus B squared. So this one we will have this expression when we solve this expression, right? So 1 divided by square root of A squared plus B squared, so multiply by the same here, so square root of A squared plus B squared, so we will have A squared plus B squared. Alright, so this is our the vector that based on the unit vector that has been derived just now. So this is the electric field intensity, so basically produced by our rho L1. So this is the expression for the electric field intensity that produced by our rho L3. Alright, so by adding all together, so this is the final expression of electric field intensity at our test point P here. Alright, so in order to evaluate the value of electric field intensity here, so by the given by this expression, so we have A is equal to 2 cm and B is equal to 1 cm. So in this case, so because of the question doesn't give us about the information on the material, so we assume that our epsilon is equal to epsilon 0 by assumption that this charge exists in the air space. So by putting all the value together inside the expression, so we will have the value for the electric field intensity on this P point is equal to x cap 1.62 kilovolt per meter. Alright, so that's all for the question number 9, tutorial 3, question number 9. Alright, so now let's look on the tutorial 3, question number 12. So in this question, we have one spherical shape or one shell spherical shape of the charge. Okay, so whereas the charge is only exists in between the radius between A until B. Okay, so the rest, so the charge is equal to 0. Okay, or we didn't have any charge that reside on that particular region, and then we need to determine the vector of D on inside our region. So whereas we have our volume charge density has been expressed by using this expression, and our vector of D, so we need to find the expression for the vector of D in the region of R less than A. So that means that inside this shell, alright, so in between A to B, so which is inside its charge itself, and at region of R is greater than B, which is the outside from this region. Alright, so similar to the previous question, so we will apply Gauss law in order to solve this problem, and this is the expression for the Gauss law. Okay, so let's consider for the first region first. On the first region, so we have R is less than A, so in this area. Okay, so because of in this area, so there is no charge enclosed in this area, so we will have the value of Q here is equal to 0. So because of the Q is equal to 0, so by looking into this formula, so we will have the value for the electric flux density as well will be equal to 0 coulomb per meter squared as well. So for the second region, so which is the region that inside this charge itself, alright, so let's see how to solve it. Okay, so first, because of the shape of this charge in the spherical shape, so we assume that our electric flux as well, it also will be produced in the spherical shape as well. So that's why the general expression for our vector of D is equal to R cap multiplied by dr. And our vector of ds, okay, so in order to put inside this formula, so also in the r cap direction, and the ds in a spherical coordinate system in the r cap direction is given by this expression. So r cap r squared sine theta d theta multiplied by d phi. Alright, so before we solve this equation, so let's look on how can we solve the q first. So this is the formula that we use in order to solve, or in order to find the total charge with the given of volume charge density rho v. So we have we need to perform a volume integration of rho v dot dv. So in this case, so we will use a spherical coordinate system. So dv in a spherical coordinate system is given by this expression. So whereas r squared sine theta dr d theta d phi, and by putting all together, so in a volume integration, so we need to perform triple integration. So the first integration is for the phi from 0 until 2 pi, so theta from 0 until pi, and r from a to r. So which mean that, so we are trying to performing a volume integration from the radius equals to a until any r point inside this charge. Okay, so that's why in this case, so we are replacing the upper limit for the r is equal to r. So this is the expression for the our rho v is given inside this question, and this is the expression for the dv. So by considering a spherical coordinate system, so by solving this mathematical operation, so we will have the expression that represent total charge. Okay, so inside the second region is given by this expression. So whereas minus rho v naught 4 pi r minus a, and the unit of it is equal to coulomb. Alright, so now let's solve this side of Gauss law. Okay, so we have closed integration of surface, so vector of d dot ds is equal to this expression. Okay, so because inside the spherical shape, so we only have one side of the surface. Alright, so we need to perform a double integration. So the first limit is from phi from is equal to 0 until 2 pi, and second is theta from 0 until 2 pi. So this is our general expression for the vector for the electric flux density, and this is the expression for the ds in a spherical coordinate system. Alright, and by solving this expression, so we will have the solution for this operation will be dr 4 pi r squared, and the unit for this is a coulomb. Okay, so because the solution for this expression is charge, and the unit for the charge is a coulomb. Alright, and then we are put all the expression together. So we have dr 4 pi r squared, which is the solution for this side, is equal to minus rho v naught 4 pi r minus a. So this one is the solution for our charge here, and so we will have the expression for dr is equal to minus rho v naught r minus a divided by r squared, and the unit for this is equal to coulomb per meter squared. And by considering our general expression for the vector of d, so this is the vector of d, the expression for the vector of d by considering the equation for the dr. Okay, and this is the expression for the vector for the electric flux density on the second region, which is r between a until b. Alright, and for the last region, so we need to consider the region that outer from our charge density. So in this area, so outer from this charge. Okay, again, so we will use the Gauss law equation. Alright, so because we have the same value of the flux value for the flux density, so this is the closed integration of surface, so the vector of d dot ds, so we will have the same value here, or the same expression as previously, because we will have the same general expression for this vector and as well as this vector, and we also have the same limit, okay, for this integration as we have been used just now. So that's why the solution for this part of Gauss law, so we will have the same expression as before. So however, for the Q, okay, so we need to perform a volume integration. So this is the limit, so we will have the same limit for the phi and the theta. So however, in this case, so we will have the limit for the R is equal to A until B. So because of, so we are trying to searching the total charge here, and the charge is only exists so between A until B. So that's why in this particular case, so the limit for R is only considered from A to B, even though the area that we are consider is greater from the value for the B. Okay, so by solving this expression, so we will have the expression that represent our total charge is given by this expression. So minus rho V naught 4 pi B minus A, and the unit for this is equal to coulomb. And again, so we are repeating the same process. So we have dr 4 pi r squared. So the solution for the first part of the for the Gauss law equation. So this is the solution for the Q. So in the end, so we will have the expression that represent our dr is equal to, or given by this expression. So we have minus rho V naught B minus A, so divided by R squared. So based on that solution, so we will have the expression for the D for each area or each region. So first is equal to 0 coulomb per meter squared in the region of R less than A, okay, which is inside this shell. Okay, so inside this charge, so we will have the expression for the vector of D, or electric flux density, is given by this expression. So R cap minus rho V naught, so R minus A divided by R squared. And in a region that outside from this charge, so the expression for the flux is given by this expression. So R cap minus rho V naught, so B minus A, so divided by R squared, and the unit is still the same, coulomb per meter squared. Alright, so that's all for the solution for the tutorial 3, question number 12. Okay, so now let's look on the last question in this video, which is tutorial number 4, question number 7. Alright, inside this question, so we are given one spherical shape of conductor with the radius of this conductor is equal to 5 centimeter, and expression or the vector for the electric field intensity on this boundary, okay, between this conductor and this air is equal to R cap 150 volt per meter. So we need to find what is the total charge that exists in the surface of this conductor. So first we need to find the expression for rho s and the expression or the value for the charge in the surface of the conductor. Okay, so by considering this boundary condition. Alright, so as we already know, so inside this conductor, so by assuming that so this is a perfect conductor, so basically the vector for the electric field intensity is equal to 0. Alright, and if we refer back on the tangential component, so we will have E2t is equal to E1t. Okay, and then because of, in this case, our expression or the value for the electric field intensity equal to 0, so that's why on the tangential component of the electric field intensity on the air is equal to 0. So that's why the vector here is only exists, or it's only represent the normal component for this electric field intensity. Under normal boundary condition, so we have d1n, so minus d2n is equal to rho s. Okay, and because of we have our inside this conductor, so our vector of E here, or the value for the electric field intensity is equal to 0. So we will have the value of flux as well will be equal to 0. Okay, so because of that, so we will have, so the normal component for the electric flux density is equal to rho s. So the dyn, or the electric flux intensity that inside this air space, okay, or air region here, is equal to epsilon naught E1n. So this is the normal component for this vector, as I mentioned just now. So because of this vector is only exists in a normal component, so we can directly replace the value of E1n is equal to 150, and this value is equal to rho s. Okay, at the same time, because of we have one charge that has been represented in a surface charge density value, so we can find the total of charge by solving this expression, which is integration for surface rho s dot ds. And by considering this is our spherical shape of the charge, so the expression of the s will be given by this formula. And by putting all together inside this expression, so the solution for the q we will have is equal to rho s 4 pi r squared. Okay, so now, so by considering this formula, so we can rewrite back this formula into epsilon naught E1n. Okay, so the rho s can be represented by this expression, so it's equal to q divided by 4 pi r squared. Okay, and we can find the q. So if we rearrange this equation back, then we will have q is equal to 4 pi r squared epsilon naught E1n, or the normal component for the vector of electric field intensity inside the air. So by putting all the value that we know inside this expression, so we will have the value for the q on the surface of that particular conductor is equal to 1.5 pi epsilon naught, and the unit of it is equal to a coulomb. Alright, so that's all for now. So should you have any further question, so please do not hesitate to ask. So that's all for now. Thank you and good luck.